hydroxide. Whereas if ammonium is an acid, if it loses a proton, it'll form ammonia, which is not hydronium. And hydronium, if it loses a proton, it forms water, not hydroxide. And if hydroxide gains a proton, it forms water. And so A is not it, even though they are related. B for sure is not. And so it is C. And a 1 times 10 to the minus, okay, this is similar, except the only thing is the molarity. If you look at that, what is that molarity? 10 to the minus 9. 10 to the minus 9 is 1 billionth, which we call nanomolar. So that's 1 nanomolar selenic acid. Is that all that concentrated? No. And so you have to figure with the acid, that dilute, most of the hydronium is going to come from, water. Most of the hydronium comes from water. So,
What dilution would water know?
Well, the most water is going to give is like 10 to the minus 7 in pure water. And so it's going to be less than that. So if you're at like 10 to the minus 5 for a strong acid, you probably wouldn't worry about water. For a weak acid, you probably should worry about water. It depends. Strong acid versus weak acid. But even at that, you might be able to push it to 10 to the minus 6, because it depends on how much error you can withstand in the calculation. So usually when you sit down and calculate it, the amount of you get from water is very small, 10 to the minus 8, 10 to the minus 9, 10 to the minus 10, And so will that have any impact? But this is already very small. This is 10 to the minus 9. And so if the most water can give you is 10 to the minus 7, that's significant, isn't it? Even if it's going to be less because of what we call the common ion. You already have product there to begin with. But if you're ever uncertain, you just do it. It takes time, but you could just do the calculation and see if you have to do that or not. This one would be difficult because here the water would perturb Ka2, and so you'd need to do it simultaneously, the second step and third step of this. All acids are Lewis, that's correct. Lewis acid is the most comprehensive definition. Bronsted is a very narrow definition. We focus on Bronsted because if we treated all acids as Lewis, we should be drawing out Lewis structures, and we should be trying to figure out the mechanism, the electrons. What we did do you guys remember what we did for CO2 and water? Do you guys remember drawing the Lewis structure for CO2, drawing the Lewis structure for water, and then identifying the acid atoms and the base atoms, and then having the attack, the two separate attacks? Yeah. I've actually asked that question on exams before, to draw how CO2 and water react. I didn't do it this time, but I've asked that in the past, so I wonder if somebody studied it or not. So, well, of course you can make it a level harder. One, can you repeat what we did with CO2 and water? And two, could you apply it to a new acid and new base? That kind of thing. That would be a level harder. Circle all amphiprotic species. Carbonate doesn't have any hydrogens. We're dealing with Bronsted.
Wait, sorry, did you do number 4?
Oh, number 4. Okay, number 4 was a partial trick question. But I didn't tell you it was trick because some people would say, okay, they did the calculation and it came out to minus 1.204 or something like that with lots of digits, right? And so it wasn't trick in that sense, that, okay, if they got minus 1.204, should they pick C or D, right? Well, both of those are wrong. Both of those are wrong because of this. What happens at 16 molar? So did you go back and look at chapter 14 and the figure? There's a little figure on that page. And they call it, what do they call it on the bottom of the figure? Uh-huh. Rebecca? There's supposed to be more of what? A greater pH? Why would there be a greater pH at a higher concentration? If you have a higher concentration of acid, you get lower pH. The lower the pH, the more acidic the solution is. And so if you have a greater concentration of acid, you should have a lower pH. You should have a lower pH. Why is C and D wrong? Because at high concentrations, what happens? Yeah, lower ionization, more what we call, what's the problem? Why is the effective concentration not the same as the stoichiometric concentration?
Oh,
Like-
that's why we need to use activity.
That's why we need to use activity, but what is the culprit behind having to use activity?
It's not acting ideally.
It's not acting ideally and doing what? It's not acting ideally, it's doing something. A lot of people don't bother, this is common, I mean, people say this all the time, and I've heard this many times. People don't read the captions of the figures because they think it's repetitive. They're thinking that the text of the chapter, and so they skip reading the caption of the figure because they figured they already read it because they read the main body. But the caption oftentimes is different. It's not a repetition of what's in the main body. And so one of the, comments that people say, to never do is never skip the figures and read the captions. So what I did was I made a little summary annotation, what this figure tells me in my own words. I don't memorize the caption. I just say what the figure tells me. So here, for example, table 14.4, I write a little annotation here telling me my interpretation of this table. That way I remember it because it's in my own words and I had to think, of what it meant to me. Could you tell me what this table means to you? Or this figure, A and B, what does this figure mean to you? Figures A. I would write a little caption here. So anyway, this is like one of these. It's like like page and a half in our book, interionic attractions. So basically, the figure is like this: we have ion pairing interactions and ion clusters. This ion cluster is going to happen at very high concentrations, and so the effective concentration is going to be a lot lower because now they're a pair, or they're a cluster, and they aren't behaving individually. And so basically that decreases the hydronium ion concentration. So if we have clusters forming, then we expect the concentration of free hydronium to decrease, and therefore the pH should be higher. The pH is measuring the free hydronium. Circle all amphiprotic. I didn't quite get to this because I didn't spend as much time on this because I covered this in Chem 1A. But does anybody remember why HF is 1,000,000 times weaker? It's 1,000,000 times weaker. This would be kind of a question you'd get like on like these are the types of questions I would prepare for on tests, like upper division, like chemistry test or something like that, Yeah, prepare for, like, why is the HF a million times weaker? Rebecca? I'm sorry? Oh, I still can't hear. Uh-huh. Break, less likely to break, but is it a million times? Do you guys remember the bond energies? I wanted you to look at the bond energies too. And remember, what I was just saying about tables, I do the same thing with the bond energies. But the bond energies, do you want to memorize every single bond energy in the table? No, what you want to do is you want to know what the biggest and the smallest is, and then say all the bonds range from that. And then you look for patterns. Triple bonds are around here, double bonds are around here, single bonds are around here. And you write a little annotation note. And then you read that. Like I would, as a student, I would have read that every day. I would read my annotation. And then by the time the test came, I had it memorized. I didn't even have to work. Like, I used to cram when I studied, and I would cram like right before the test to try to get into my short-term memory. But that wasn't so easy. And so I gave up on cramming. And not only that, cramming was too stressful for me. I couldn't handle the stress of cramming for tests. So, after I started doing that, I was much more relaxed. Like before the day of the final, I didn't have to cram, and then before the final exam, I didn't really have to cram because I already had everything memorized. I just wanted to do the highlights stuff. You could try that, or you find some other way. If this last exam didn't go as well as you expected, maybe some tweaks to your studying. You might be putting in the effort, but maybe a tweak here or there might prove to be the key. And then people have, obviously everybody's different, so when I took biochemistry, I got like a 25-page packet of how to study for biochemistry. And actually I followed it, but it didn't work so effectively for me because he said to read the chapter 5 times. I couldn't read the chapter 5 times. I didn't have enough time to read that many times. He said, what was it, 2 times before lecture, 3 times after lecture. If you have it must be a fast reader. I'm slow. But so I was watching these YouTube videos about how to speed read more recently. I have a lot of unread books. So the problem is, Rebecca, if you said that, that the bond is stronger, then we would want to back it up with some data. If this were take home. See, bond enthalpy. So I wouldn't even be all that precise. I'd just say bond energies range from about 100 to the strongest one here is 946. The weakest is about 150. So 100 to 1,000. Triple bonds, like I'd compare the 2 triple bonds, 900 and 940, so around 1,000. Double bonds, 600. Single bonds, most of them are around 300 to 400 range, and that's it. But when we look at HF is 565, HCl is 431, HBr is 364. HBr and HCl are strong acids. HI is 297. So we go HI 297, 364, 431, 565. That just seems like an even trend. But HF is significantly stronger of an acid, so that doesn't explain it. Yes, it's more polar, it has a more polar covalent bond, and it is stronger. Fluorine's smaller, so it's a stronger bond, but it's not a million times stronger. So it doesn't explain it. What happens is this. You have very strong ion pair formation. We're talking about ion pairing. And I remember at UCSB, when I was at UCSB, I was a teaching assistant for the Chem 1A there. And I remember on the test, you threw out a question about, I think it was benzoic acid. It was that if you have like a 1 molar benzoic acid solution, the exam question went something like this. I don't remember it exactly, but it was similar to this. A 1 molar benzoic acid solution has an effective concentration of 0.5 molar. Explain. And I remember that question vividly because I thought, wow, obviously the professor never talked about it. But I knew the answer, right? But when I looked at the tests that I was collecting, there were a lot of blanks there. Do you know the answer? Why? And then I thought, I didn't even think they discussed it in the book. And I don't think he talked about it in the lecture because the students were complaining after the exam about that particular question. But we have ion pairing interactions, these ion pairing interactions, and the problem with HF is the ion pair is too strong. Fluoride's very small, and so it has a very strong attraction, and therefore the HF, you break the bond, but they don't completely separate. And so it requires an additional collision to get them to separate. And so this is at the end of the chapter. And so looking at the chapter, what was it? So they showed again, and so you would have made a connection. If you remember the figure from, here they talk about the bond energies. So already I should have went here. 565, 431, I remember. Already you would have connected it. And so this ion pair formation is like what we're looking at, those ion clusters, ion pair formation from chapter 14. So we end up forming an ion pair. That ion pair has to be broken apart. So water will try to pluck off the proton, but then it can't completely escape fluoride. And so it forms the ion pair. When we have the ion pair, then the hydronium can't effectively neutralize other bases. And therefore it's going to be a much weaker acid than you expect. And versus the others where the hydronium can easily escape chloride, bromide, and iodide, because chloride, bromide, and iodide have much lower charge density. And so you aren't going to have such a strong electrostatic attraction, the electrical attraction between positive and negative. And you've got this ion pair formation here. And then it takes another collision to break the ion pair apart. And so the ion pair reduces the effective concentration. So the effective concentration for HF is much lower than the stoichiometric concentration, and therefore it's a much weaker acid than all those others. Ion pairing is not an issue with the chloride, bromide, and iodide because those are quite big and not so dense in negative charge. Amines are bases, analogs here. Methylamine, we talked about some amines here. The same thing here. These benzene rings are weird because they're hydrocarbons, but they're electron withdrawing. They're electron withdrawing because of the pi, delocalized pi bonding network and the possibility of delocalizing electron density into the ring itself. And so that makes this a lot less basic. Normal amine like these with the electron pushers are a lot more basic. This is a lot less basic because of the electron withdrawing effect of the ring. So we can see that in the pKb's. The lower the pKb, the stronger the base. And so cyclohexylamine is a much stronger base, 3.36, versus aniline, which is 9.13. Are you guys familiar with these skeletal structures? Yeah. In organic chemistry, we just show the carbon-carbon bonds and eliminate. These are sp3 carbons here. There are 2 hydrogens bonded to each of these. These are sp2 carbons here, 1 hydrogen bonded to it. And then remember the chloro and the para. And in this case, the closer it is, the better, because Coulomb's law, electrical interactions weaken with distance. So this is talking about ortho and para and meta substituted amines. And then we look at the stability of the bases here. All right. So that pretty much finishes chapter 17. There, but there's still one more thing I wanted to talk about, chapter 17, but we'll do it after this. So this is just knowing, the conjugate relationship here. So if you have a pKa of 371, its conjugate base will have to be a pKb, so that pKa and pKb of the conjugate pair adds up to 14. So this is just 14 minus 371, it's 1029. Which acid is strongest? Okay, this is electron withdrawing, this is electron pushing. So we want more electron withdrawing. That's going to make the hydrogen more blue. And so trichloroacetic acid. In fact, trichloroacetic acid is, some people call it a strong acid. The percent ionization of hydrochloric acid decreases as concentration increases. No, we treat the percent ionization of hydrochloric acid as 100% at all concentrations. It's a strong acid. And so K is very large. This is a one-way reaction. It doesn't behave like a weak acid. Which species is more basic? And so this is definitely not very basic because of the electron withdrawing group here. And then benzene, you'd expect this to be the most basic because it has the biggest hydrocarbon, and hydrocarbons are electron rich. However, this is not a normal hydrocarbon. This is what we call an aromatic hydrocarbon. That is, it's got this delocalized pi bonding network, and this is benzene. This is a benzene ring, C6H5, O minus. So this is electron withdrawing. This is severely electron withdrawing. This is mildly electron withdrawing, and then we get delocalization, and so that would be significant, actually, the delocalization of the negative charge into the ring itself. And so A's got to be it. There's no delocalization here. There's no inductive effect. Which species is the strongest Lewis acid? I screwed this up because I had it Lewis base, and so I gave everybody 2 points for that. Which solution should have the highest pH? The highest pH, phosphate's the strongest base out of here. So this is acid, ammonium, nitrate's neutral, sodium's neutral. Chloride's supposed to be a base, but it's too weak to hydrolyze water. So this is neutral. Phosphate's a base, and fluoride's a base. And which one's a stronger base? Phosphate, by far. Phosphate's pretty moderately strong as a base. The percent hydrolysis is actually pretty high for phosphate. Which base is expected to be strongest? So we're looking at some nitrogen containing. And so this electron withdrawer is going to make it less red. And then this should be basic for sure, but we have hydrogen here. Versus a methyl. A methyl is electron pusher, electron rich, so this will be more basic than ammonia. And this has two methyls on here, dimethyl. Dimethylamine is going to be the most basic. But you have to be careful because there's some weird stuff that can happen, you know, that this is what we predict. However, if you go to trimethylamine was conveniently left out of this. This was, I think, from the homework. I noticed they didn't put trimethylamine in there because trimethylamine kind of screws things up because trimethylamine is actually, you'd expect it to be stronger yet, you know, because with another methyl group. I think the Kb on trimethylamine is actually weaker than dimethylamine. And so there's other reasons too. The other reasons you get into, you know, because sometimes base strength depends on free access, you know. If it becomes too bulky, the nitrogen's the base atom. And if you have these bulky groups attached to the nitrogen, it inhibits, you know, it from attacking acids. It's called steric hindrance. Steric hindrance you get into in organic chemistry. We don't look at it here, but that could be one of the reasons. I'm not sure. But we'd have to look at other factors that influence, and there are multiple factors that can influence it. Like the most important factor is bond strength, but here all the bonds are the same. They're all HO bonds. 496 or 3, I forgot. So you don't have to know that, you just ballpark it, you know, 300, 400 kilojoules per mole. So they're all the same roughly. And so which one is going to be the most blue? The most blue is going to be this one because of the inductive effect. Fluorine's more electronegative. But would you use electronegativity to argue number 14? Fluorine's the most electronegative. No, you wouldn't use electronegativity. What would you use to argue for number 14? Size and bond energy. Yeah, this is for sure the weakest bond here, HI. Sodium fluoride, fluoride's a base, and so the pH has got to be base, you know, greater than 7. The pH of water, 25. Above 25, we expect more hydronium or less hydronium? More collisions or fewer collisions? More collisions. We're going to shift, what's that distribution called? That shows the energy versus population. Maxwell-Boltzmann distribution. Or the thermal distribution. A lot of people just call it the thermal distribution. The Maxwell-Boltzmann or thermal distribution. Thermal distribution shows up over and over again. So that's the only reason why I'm asking you to remember the name. So we expect more collisions. More collisions is going to generate more hydronium. More hydronium means the pH goes down. Fortunately, modern pH meters have what? This is something I said in the lab. Modern pH meters, did you measure the temperature of your solution before measuring the pH? You didn't, because modern pH meters have a built-in... Yeah, they automatically recalibrate for temperature. And so it's a temperature correction, they call it. And so it stays 7. Even if the temperature fluctuates for pure water, it'll stay 7. But in reality, it doesn't. You know, in reality, the pH fluctuates with temperature. What is the percent ionization of 0.100 molar acetic acid? Well, it's a weak acid, so you can eliminate A and B. Well, maybe B. It's got to be B, C, or D. And so you just pick the... You could have taken a guess, although these are kind of close. Or you just do the calculation. This is just the ice table. You don't have to worry about K W because, it's 0.100 molar is fairly concentrated. And it's 10 to the minus 5, which isn't the weakest of weak, This is 1.3. So you do a quick ice calculation here. Figure it out. What is approximate pH of 10 to the minus 10 molar? 10 to the minus 10 molar HCl is so dilute. I said I'd drink it. Does anybody recall? I'd probably drink, 10 to the minus 8 molar. Right. It's so dilute, and so the pH is about 7. Oops. But you might say, I claim I would drink it, but would I really drink it? It's like, I remember in my high school chemistry class, the chemistry teacher always said, he'll drink the HCl, but first he has to mix it with sodium hydroxide. But he never did drink it. So I'm guess guilty of the same. So this is a KB equation. We have the Ka equation. I think most people got this, no problem. Which is good, because in the past I've asked KB equation and people give me amide or other things, KB is base hydrolysis to form hydroxide, but it's not dissociation of ammonia. And so oftentimes I get H plus and amide a lot. This is just stepwise works fine for this. Essay fails. We use quadratic. I didn't complete the key. I need to complete it. Well, those are the multiple choice. I'll pass those back today. All right, chapter 17. Chapter 17, internal storage. Chapter 17 is just acid plus water or base plus water. That's it. Acid plus water or base plus water. Although some of the salts they didn't really talk about. Chapter 17 gets into more complicated mixtures of acids and bases. So let me give you one from chapter 17. In chapter 17, they talked about salts solutions, but they didn't talk about all salt solutions. Do you know what salt solutions they didn't talk about? Did they tell you what salt solutions they didn't talk about? They talked about acidic salts, I think. Acidic salts would be ammonium, analogs. It could be R3N, or a lot of people will do R, like this, and then they'll do R prime and R double prime. The three R's don't have to be the same. And this is where R is a carbon, chain, or hydrogen. And that'll keep it in a mean, because carbon and hydrogen, the En for carbon is a 2.5, the En for hydrogen is a 2.1. And so it keeps it in a mean type behavior. If you put a more electronegative, like a fluorine, then no go is an amine. And so these are called amines here. And so what we need is, this is a base here, but we can make its conjugate base, actually, conjugate acid. Actually, this should be like this. These are amines here. Amines are bases, but we can form cations by just adding an H plus here. If we add an H plus, then we're going to get R, like, for example, R3NH, and now we have to have a positive charge on it. And the same thing here. We take that lone pair and convert it into a bonding pair, and so we end up with this. These are acid cations, and the Ka for these is going to be about the same as the Ka for ammonium. More or less, but about the same as ammonium. It depends on the R group. methyls are more electron rich, and therefore if we put methyls on there, we expect the Ka to decrease. The Ka should decrease if we put electron rich species on there. And so an example of this would be ammonium chloride. And then we had basic, the basic ones, we just look at the chart over there. And so the basic one would be like sodium carbonate, or potassium fluoride, etc. But in chapter 17, we're going to deal with more complicated salts. These are skipped over in chapter 18. These were skipped over in chapter 17, these more complicated salts. The more complicated salts would be, what if I had ammonium carbonate? Well, ammonium is acid, carbonate is base. And so what do I do? Well, if I have an acid, then I would do Ka for the acid. And so that's no big deal. This is a standard chapter 17 problem. This is going to generate hydronium and ammonia. But I also have base in there, so I have to do Kb for the carbonate. And maybe Kb2. So there are two ways to approach this. The first approach would be qualitative. We compare the Ka with the Kb. If the Ka for ammonium versus the Kb1 for carbonate, we see which one's bigger. If Ka for ammonium is bigger than Kb for carbonate, then the pH should be less than 7. If the Kb for carbonate is bigger than the Ka for ammonium, then the pH should be less than 7. If they're about comparable, then the pH is around 7. The other approach that we would use is quantitative. Let's say I want the pH. I don't want this kind of approximate range. I want to know what the pH is. How would I do that? Uh-huh.
Wait, so whether Ka is greater or less than Kb, the pH is still going to be less than 7?
If the Ka for ammonium is greater than Kb for carbonate, we produce more hydronium than hydroxide, and therefore the pH should be less than 7.
So it's just less than 7?
No. If the Kb, oh, okay, this is the problem. The problem is one has to be greater than, this second one, sorry, is greater than 7. Okay, then the other approach is quantitative. we cannot solve these independently of each other. Because the hydronium concentration and hydroxide are tied together in a seesaw relationship. If one goes up, the other has to go down. Are tied to one another by Kw. So we've seen this kind of problem before. We can't solve this stepwise. We can't solve them independently. We have to solve them simultaneously. So we must solve this simultaneously. The Ka for ammonium plus the Kb for carbonate and Kb2 plus, actually Kb1, 2, I'll just say, plus Kw. At least 3, 4 in this case. But solving 3 or 4 is that easy to do? No, this is very difficult. So it's best your book skips it, right? Because it's going to be very difficult. And so they don't even talk about it, I think, here. So that's one complication, more complicated salts here, where we have an acid and base in combination. In chapter 18, it doesn't even have to be a salt. You know, we could just have a weak acid and a weak base together. Very difficult. In chapter 18, we're going to see this type of scenario, and we'll also see things like this. Like, for example, if I had ammonia and acetic acid, you know, this gets complicated as well. Weak acid-base mixtures are complicated. This is a weak acid-base mixture because the cation is the acid, the base is the anion. All right, so that's one type of salt that was skipped over in chapter 17. There's another type of salt that was skipped over in chapter 17. I'll talk about that now. The other salt that's missing from chapter 17 are the amphoteric salts. The amphoteric salts would be like sodium bicarbonate. And the problem is bicarbonate's both an acid and a base. We've dealt with amphoterics before, like when we were looking at phosphoric acid, we dealt with amphoterics, but we didn't have to worry about one end. You know, if it's an acid solution, we only look at Ka. We ignore Kb. The reason we ignore Kb is because we already did the equilibrium for that, just in terms of hydronium rather than hydroxide. But if we have an amphoteric salt alone, then we have to worry about these two collisions occurring. The two collisions occurring would be bicarbonate as an acid collides with water to form hydronium and carbonate. And then the other collision that occurs is bicarbonate plus water forms carbonic acid plus hydroxide. So we can't stop these two collisions occurring. You know, they're going to be happening at random, although one of these is more favored. Like bicarbonate, the acid collision is more favored than the base collision, but both collisions occur. And so do you know what you have to do in a situation like this? Can you solve for one and then solve for the other and cancel them out? I mean, you could try that as an approximation, but this is best solved what? So qualitatively, you could do this. We could do the same thing. Qualitative, we just look at which is bigger. Just compare. If Ka is bigger than Kb, then the pH should be lower, and this is more acidic than basic. And the Ka is bigger. Quantitatively, how would we do it? So here we just compare the Ks. Quantitative, we have to do what? Do you know what we have to do if I want quantitative? We have to solve Ka and Kb simultaneously. Not only Ka and Kb, but what ties hydroxide and hydronium? Kw. So we need to do Ka for bicarbonate and Kb for bicarbonate and Kw simultaneously. Okay, when we look at this and we compare which one is more difficult to solve simultaneously, which one would you guess would be more difficult to solve simultaneously? A mix like this, ammonium and carbonate? Well, for sure this one would be because of Kb1 and Kb2, but let's just say we had a Kb. It was like ammonium acetate. Or this. Well, it turns out this one's easier to solve. And can you tell why it's easier to solve? Because the acid and the base are the same species. Whereas the previous problem, the acid and the base are different species. The acid being ammonium and the base being carbonate. So somebody else did it. After doing all the work, they didn't solve it for a specific answer. Sometimes we solve things for an equation. We don't always solve things for a number. And then people complain, well, I don't have all the data to calculate a number. Sometimes you don't want a number. You know. sometimes we solve things for an equation like, which is more powerful than an individual number, because an equation will give us a whole range. Think the Schrodinger equation. How many orbitals are allowed in a hydrogen atom? Do you know how many orbitals are allowed? Or how many orbitals are there in the hydrogen atom? Some people tell me there's only one orbital in the hydrogen atom. It's the 1s orbital. Yeah, but an orbital is an allowed state for the electron. So the 1s is the ground state, but there are how many excited states possible for the hydrogen atom? Rebecca. 8? 8? Like the 1s, the 2s, the 2p, 3 of those. And make an octet. 8 would give us 16 electrons or something. No, more. In order to ionize an electron off the hydrogen atom, we take an electron from the ground state, the 1s orbital, and promote it to what state? Well, not just any excited state. We promote it all the way to the highest excited state. What is the highest excited state? What is the n equal to for the highest excited state? N varies from what? 1 to... I know somebody who's studying for the MCAT. I'm going to help them pretty soon. But they probably forgot too. I don't know if the MCAT actually asked this kind of stuff from quantum. Nobody remembers? N varies from 1 to infinity, yeah. That's good, Alexa. I mean, if you forget, you just take your best educated guess. Infinity's it. It's infinity. So there, we don't want to solve. Do you want to solve an infinite number? No, it's impossible. So what they do is they solve the Schrodinger equation for equations. And so you're taking the Schrodinger equation and you're solving it for equations. Those equations are, and they didn't show it, but the equations are where the quantum numbers come from. And so after doing simultaneous here, we solve it for an equation. And we come up with actually a fairly simple equation. For amphoteric species, the pH of the amphoteric, this only works for amphoteric because the pH of the amphoteric is equal to the pKa for the amphoteric plus the pKa, I wrote this before, but I was kind of pressed for time, the conjugate acid of the amphoteric divided by 2. And so it turns out to be a very simple equation. And that saves us from having to do the simultaneous work. So if somebody solved it for an equation, we can use that equation. Just like somebody solved the Schrodinger equation for an equation, and we can use that equation. It makes our life a lot easier. It's like an engineering equation, here. And you might think, you aren't going to have to derive this equation because it's just too much. And they use the simplifying assumption. And so there are some constraints to this. In order to generate this equation, the simplifying assumption had to work. In order for the simplifying assumption having to work, you have to have a decent concentration. That is, if you had 10 to the minus 10 molar amphoteric solution, then we know the pH is not going to equal this. If you had 10 to the minus 10 molar amphoteric solution, what should the pH equal, roughly? 7. So this equation is going to fail. This equation fails at very dilute concentrations because the simplifying assumption is going to fail. For very dilute solutions. Well, what is very dilute? Dilute depends on what the amphoteric species is. And so we aren't going to worry about it too much. We're just going to hopefully have a decent concentration of amphoteric, like 0.100. You don't have to worry too much about it. But if somebody gives you a ridiculous concentration like me would give you, like 10 to the minus 10 molar, then it would fail. Okay. So equation fails for very dilute solutions of amphoteric species. Because the simplifying assumption needs a hold. We're not going to justify it. It would be nice to justify it, but we're not. We're just going to cross our fingers and hope it holds. So I'll just say needs to be valid. No, we don't justify it. No, we are not justifying. So we don't have to prove it. So whenever we have an amphoteric, it turns out to be easy to figure out the pH. But if we have, the amphoteric is easy because the acid and base species are the same. But if we have different acid and base species, then it becomes a much more complicated question. And so in chapter 18, we're going to look at mixtures. And so let's take a look at mixtures. Of acids and bases. There are 3 major ones that are discussed in chapter 18, but there are more. Obviously, there are many more. 3 major ones. So, for example, this one I talked about here with the salt that's acid and base. This acid-base salt is completely skipped over in chapter 18 because they aren't going to talk about this more complicated simultaneous. And so the 3 major ones that we're going to do are the common ion mixture. We've already done sort of this already. The next one is a buffer mixture. But a buffer is a mix of weak acid and weak base. Weak acids and bases, let's just say that. So a buffer is a mix of weak acids and weak bases. If the weak acid and the weak base are different, we're going to kind of ignore it. If the acid and base are unrelated, then we have to use simultaneous. And the book doesn't want to get into simultaneous, so the book ignores these, basically. And so that would be like ammonia and acetic acid. We're not going to worry about calculating pH for that, because that's all simultaneous. However, if the acid and base are conjugate pairs, then this is a special type of buffer. So if the acid and base are conjugate pairs, then it's a special type of buffer. And this special type of buffer is called the Henderson-Hasselbalch buffer. And then we could have the acid and base being the same thing. Where have we seen where the acid and the base are the same thing? This is amphoteric species, which could have some type of buffering action. But the behavior is quite a bit different than the Henderson-Hasselbalch buffer. We're only going to talk about this, the Henderson-Hasselbalch buffer. That's the easiest. And we don't have to deal with simultaneous. The last type of mixture that we're going to cover in this chapter is the titration. You know, where you take an acid and try to neutralize it with a base, or take a base and try to neutralize it with an acid. So it's just acid-base and a neutralization. But the titrations aren't all neutralization. So let me talk about common ion mixtures first. For common ion mixtures, we have to worry about Le Chatelier's. Le Chatelier's principle. Some things are not perturbed by Le Chatelier's principle. So there are a whole bunch of examples of common ion mixtures that they look at in the book. One type of common ion mixture would be something like this. I'm going to take some hydrochloric acid, like this, and mix it with some sodium chloride. And so one of the ways we could break this down is like this. Let's go with 0.1 molar hydrochloric acid and 0.1 molar sodium chloride. And so what I'm going to do is this. Will sodium chloride neutralize my hydrochloric acid? You think? It doesn't neutralize it. And what I'm talking about is something like this. So sodium chloride is what we call a soluble salt. Soluble salts are strong electrolytes. Strong electrolytes ionize or hydrolyze 100%. So the sodium chloride will be ionized like this. So I might start off with 0.1 molar and 0 molar here. And then there's going to be a change. The change is going to be complete, minus 0.1 molar. And I end up with 0 molar. And I get plus 0.1 molar here, plus 0.1 molar here, and then I end up with 0.1 molar sodium ions and 0.1 molar chloride ions. So I'm going to call this step 1. No problem. K for this is very large. Soluble salts. Then I go to step 2. Step 2 is HCl. And so I have HCl here, and HCl will hydrolyze water completely. That's going to form hydronium and chloride. And what I'm going to do is I'm going to take the chloride that I generated from step 1 and drop it into step 2 here. So what I'll do is I'll just do the standard. The standard is we're going to assume nothing has hydrolyzed yet, and so there's 0 molar hydronium. However, I'm going to have 0.1 molar chloride from the previous step here. Now, normally when I have product here, I don't get as much hydrolysis, right? And so we'll having product here, this is called common ion. Having common ion here inhibit the forward reaction here at all? And the answer is no, because K is very large. Very large is just one way. And so K very large is not perturbed by Le Chatelier's. So you might think it'll be less acidic. Less acidic means it's partially neutralized. No, that's not going to happen. What's going to happen is it's going to be fully acidic because we're just going to go ahead and hydrolyze all of it. And so we're going to end up with plus 0.1 molar here and plus 0.1 molar here. And so what we end up with is 0.1 molar hydronium and 0.2 molar chloride. And so when we look at the species present are going to be 0 molar HCl, 0 molar sodium chloride, 0.1 molar sodium ions. Oops, this should be a different color. Just trying to make this a different color. And 0.2 molar and 0.1 molar hydronium. So did having the common ion here perturb step 2? No. However, what if I did this? In the next example, I'm going to have acetic acid. Do you know the abbreviation for acetic acid? HAC. I'm going to use this abbreviation because I don't want to write out the formula for acetate. I assume everybody knows it already anyway. Right? This is where AC minus is equal to, give me the two ways of writing acetate. C2H3O2 minus, or what's the other way of writing acetate? The condensed structural formula.
CH3CO.
Yeah, this is the condensed structural formula, CH3 COO minus. I don't want to write either of those, so I'm just going to write HAC plus water. Oh no, I'm jumping ahead, sorry. HAC and sodium acetate. Now this is going to make a difference. So what we do is we start off with the biggest first. So I'm going to start off with sodium acetate. Sodium salts are all soluble, so they ionize completely into sodium ions and acetate ions. K is very large. And so I'm going to do the same, 0.1 molar here. So, you know, your book skips the ice table for this, which is fine. But I'm just going to go ahead and write the ice table even though. You probably can do it in your head. Or if not, it doesn't take much time to figure it out. So I'm going to end up with 0.1 molar sodium ions and 0.1 molar acetate. Well, if we go on to the next step will be acetic acid and water. This is going to change the acidity here significantly. So initially I'm going to have 0.1 molar. I'm going to assume nothing's hydrolyzed yet, and therefore I have 0 molar hydronium. But what I'll do is I'm going to drop the acetate down. So this is the common ion here. And the common ion here means I'm going to have a lot less hydronium. Why will I have a lot less hydronium? The reason why is because I already have 0.1 molar acetate. That's a lot of acetate. So X doesn't have to be nearly as big. So I'm going to get 0.1 minus x molar. I'm going to get x molar here and 0.1 plus x molar here. And so when I do this, you know, the Ka for acetic acid is 1.8 times 10 to the minus 5, which is equal to the hydronium concentration times the acetate concentration divided by the HAC concentration, which is equal to x times 0.1 plus x. And so it's not x squared up here, it's 0.1 plus x, which means x can be a lot smaller, over 0.1 minus x here. And when we try the simplifying assumption, etc., we go on. But the point here is the common ion will do like a Le Chatelier's type shift. You know, when you have too much product, it shifts it to the reactant. Well, we have to shift this to the right because we have a 0 here. And so this reaction has to go to the right, because we can't go below 0. We can't go negative. But it's not going to go very far to the right because we already have a lot of product here to begin with. And so this I call Le Chatelier's inhibition. It's not a Le Chatelier's shift, but Le Chatelier's principle is inhibiting the forward reaction. Does that make sense for this particular one? And so this is the common ion effect. The common ion effect means that the shift, the reaction is going to be lessened, the percent reaction. So if we do the percent ionization here, you know, the percent ionization normally is around 1.3% for like 0.1 molar. However, the percent ionization here, that is the percent reaction, x over 0.1, is going to be a lot smaller, a lot smaller than 1.3% because of that. And so we're going to get a lot less. And therefore, this should be a lot less acidic. It makes sense because sodium acetate's a base. So if you add base to an acid, the pH is going to go down, right? It doesn't completely neutralize things. We're lucky here. Because normally when we add a weak base, we have to do Kb for the base and Ka for the acid. But you see, this one equation takes care of that. Because you might say, why didn't I do the Kb for the base? Why did I do the Ka for the acid? Because isn't there one more equilibrium? Isn't there one more equilibrium? And that is acetate. You know, I generate a lot of acetate from sodium acetate. And so acetate plus water is going to give me acetic acid and hydroxide. Why am I ignoring acetate's collisions with water? I have acetic acid's collisions with water, but I have plenty of acetate in there. In fact, I have equal amounts of acetate and acetic acid. So why am I ignoring acetate's collision with water? And what would you tell me the answer is? Why am I ignoring acetate's collision with water? I already solved for it, right? I already solved for it. This would be redundant. I don't remember solving for it. Where did I solve for it? Maybe I solved for it last week. Did I solve for it last week? No, I didn't solve for it last week. So where did I solve for it? I solved for it in the Ka here. Because the Ka describes the equilibrium between acetic acid and acetate in terms of what we say pH. Hydronium. Kb solves for the equilibrium between acetate and acetic acid, but instead of in terms of pH, in terms of the POH or the OH. And the pH and the POH are related by pKw. So the real answer is I could have used either. I could have done KB or KA. Either one would have been fine. However, since I have acetic acid in there, I'm just going to use Ka to solve this. Because if I did this, I would do one more step. The one more step would be to convert POH to pH, and I'd get the exact same answer, and I'd get this exact same equilibrium concentrations. And so this is why I call it redundant. This is different than the amphoteric, because in the amphoteric species, they are not redundant. You have to do both Ka and Kb because there's no other equilibria present that we've done before. All right, so this is the common ion. When we have an acid solution like this, well, this is an acid and a base solution, but we're lucky because this acid and base solution are related. This common ion solution is very special. This common ion problem, the second common ion example, this example equals what we call a Henderson-Hasselbalch buffer. Henderson-Hasselbalch buffers have the form of this. It's going to be a mixture of X molar HA. Now, A is different. A is a generic anion. AC is acetate. A is a generic anion. And so we're going to have X molar HA plus Y molar A minus. That's a Henderson-Hasselbalch buffer. We need both present in significant concentration. Both must be present initially in significant concentrations. In other words, we can't just have HA and say, okay, it's going to collide with water and produce A minus. That amount of A minus is too small to classify as a buffer. Oh yeah, okay. I'm going to stop here. And,
Wait, can you go back to the last one?
somehow it got cut. Let me undo it. Let's see if it undoes. Yeah, it undid, I think. Oh no, it didn't undo. I just have your Scantron.